Hey everyone, the objective of this video is to use reference tables to predict products of single replacement chemical reactions. To begin, when one element replaces another element in a compound, a single replacement, also known as displacement reaction, has taken place. When this happens, a new compound is formed and an element is released. The general formula for this is A, which would be the element, combining with Bx, which would be the compound, is yielding Ax plus B, which is now a free element. So you can see that A is taking the place of B so that it becomes Ax. So a single replacement reaction will only take place if a more reactive element is replacing a less reactive. So back to this example, A must be more reactive than B in order to free up B so that it is now free. So here's a simplified definition. A single replacement reaction is a reaction in which one element replaces another in a compound. So here we have calcium replacing the potassium that is within potassium chloride, and it becomes calcium chloride and free potassium. And here's another example right here where we have iron, free iron is replacing the lead of lead nitrate, producing free lead and iron 2 nitrate. So now the question is this: how can I tell if that reaction will take place? And the answer comes from this right here. This is in our reference tables, and it's called an activity series. What an activity series will do for us is it will identify the more active metals and the more active nonmetals. So let's just say, for instance, if we have zinc in a compound. So zinc in a compound with, let's just say, X. X is some variable. And as a free element, we have magnesium. So magnesium versus zinc X, whatever it is. Will the magnesium take the place of zinc? And if we take a look at this table here, magnesium is higher than zinc, meaning it is more active, and therefore magnesium will take the place of the zinc as such. Now, in the event that we have to explore the nonmetals, the same is also true. Okay, if fluorine is freed up and chlorine is involved in the compound, well, fluorine is more reactive than chlorine. It would take the place of it. So now let's try to apply this. Here we have a situation where we have silver in combination with potassium nitrate. Will the silver, which would normally become a positive ion, take the place of potassium, which is also the positive ion? And to understand this, we find where silver is on this chart. Silver is right here. And where is potassium? Potassium's much more reactive, so potassium will not give way to silver. And we say, in that case, that there is no reaction. All right, let's look at another. Zinc. Zinc in combination with silver nitrate. Zinc lives, where are you, zinc? Zinc is right here, and silver again is right here. So zinc is more reactive and will take its place. So what will that look like? We have zinc, NO3 nitrate, and free silver. But we have to consider something else as well. We have to say, is this balanced. Now we know that zinc, let me show you zinc. I have it right here. Zinc, where are you? Zinc is right here. And if you notice, there is a +2 with zinc. Let's get this out of our way. Now zinc likes to have a plus, not grabbing the pen, there it is, a +2. And nitrate, which is a polyatomic ion, I'll show you that, NO2. Sorry, was that NO2 or NO3? NO3. NO3 has a -1. Let's get that out of our way now. So a -1. So from our work in the past, we would know that what we have to do is we have to increase the number of nitrates by 2 using that crisscross method. But that then uncovers a new problem. On the left side we have 1 zinc, on the right side 1 zinc. On the left side 1 silver, on the right side 1 silver. On the left side 1 nitrate, NO3. On the right side 2. So we do have to balance it. So what if we were to double up the number of silver nitrates? Well, that's well and good. It does balance our nitrate, but it now doubles up on our reactant side the number of silvers. And that's easily adjusted by saying that we have to have 2 moles of silver on the product side. Let's reinspect. On the left we have 1 mole of zinc, on the right 1 mole of zinc. On the left 2 moles of silver, on the right 2 moles of silver. On the left 2 moles of nitrate, on the right 2 moles of nitrate. It all balances. Really nice now. Let's try just one more of these. And here we have aluminum with H2SO4, which is also known as, if it is dissolved in water, hydrochloric acid, okay, or hydrogen sulfate. Now, aluminum. Aluminum on this chart is right here, where hydrogen is right here. Aluminum is more reactive, so aluminum will take the place. So it would be AlSO4 plus H2. Now, again, I am curious, is it balanced? I'm just taking a look at my cheat sheet and what I did a little bit earlier. Good, let me show you how this works. Aluminum is right here. Right here. And there's a +3. And from our polyatomic ions, well, before I forget, I'll put the +3 in. +3. And from our list of polyatomic ions, we would see sulfate, SO4. SO4 is right there, and that's a 2 negative. So let's put that in. -2, 2 negative, really the same thing. If we do our crisscross method, drop this 2 down here, drop this 3 down here, it becomes Al2, SO4, but we need 3 of them. Now let's see if this balances. We have 1 mole of aluminum on the left, but 2 on the right. 2 moles of hydrogen on the left, 2 moles on the right. That looks good. 1 mole of SO4 on the left, 3 moles of SO4 on the right. So to start my balancing, I'm going to put 3 moles of H2SO4. That way we are balancing SO4 with SO4. I am also going to balance my aluminums by just giving myself 2 of them on the left. But what do I have to do with these hydrogens? We have 2 moles of hydrogen on the product side and a total of 6 moles of hydrogen on the reactant side. And to balance that, I would put a 3 here. And there we go, we got it. Now let's take a look at a couple more. Here we have 2 moles of chlorine, actually 1 mole of the molecule known as chlorine, which has 2 moles of chlorine atoms to build it, combining with 1 mole of potassium iodide. Now chlorine's a nonmetal, so we're going to start looking over here for that. And chlorine resides right here, pretty high to the higher activity. And iodine is right here, lower. So will chlorine take the place of iodine? And of course the answer is yes. So we have potassium chloride. And, well, first of all, should it combine with 1 potassium to 1 chlorine? In order to understand that, let's quickly take a look at them. Okay, potassium is right here with a +1. Chlorine is here with a -1. So the answer is absolutely yes, because potassium would become a +1 while chlorine a -1. It has to combine in a 1-to-1 ratio. And what will be left over? The potassium is now with 1 chlorine. So now we have some free iodine. Now let's see if this balances. We have 1 potassium on the right, 1 on the left, 1 chlorine on the right, 2 on the left, 1 iodine on the right, 1 on the left. Now how would we balance this? Well, I definitely need to double up on my chlorines, but that increased my number of potassiums at the same time, so I am going to need to increase that. Inadvertently, that increased my number of iodines. So what happens if I increase this? Now let's quickly inspect. On the left I have a total of 2 moles of chlorine. On the right, 2 moles of chlorine. On the left, 2 moles of potassium. On the right, 2 moles of potassium. And on the left, 2 moles of iodine, 2 moles of iodine. It works. This next one, we have lithium. Lithium versus hydrogen. And I do not see lithium here, nor hydrogen, or oxygen for that matter. So lithium is going to potentially take the place of the hydrogen. Lithium is the most reactive, so there we go. Lithium must replace oxygen. So lithium will then be with the oxygen, and the hydrogens would be free. Now, does this balance? Lithium and oxygen. Here is lithium at +1, oxygen at -2. So we are going to have to do a little work on this. This is a +1, this is a -2. So we are going to have a formula of Li2O to make lithium oxide. How does that affect our balance? Well, we have 2 moles of lithium on the right, only 1 on the left. So let's adjust that right now. We do have 1 mole of oxygen on the right, 1 on the left, 2 moles of hydrogen on the right, 2 on the left. She balances, looks good, and I hoped that this video helped. Well, you know what? There's time for just one more. Why don't you pause this one? Try it yourself. Alright, now let's inspect. Here we have copper, which is a metal. There's iron. That's sulfate. It's a polyatomic ion right here. Will the copper take the place of the iron? Copper is right here. Iron is right here. Which one is more reactive? Iron is more reactive, and it is already part of the compound. So here we will have no reaction. Bye now.